Hello, welcome to this new lecture of the course Transportation Network Analysis. So, in the last class, we were discussing about extension of the user equilibrium when there are link interactions between various links. So, we had started to discuss this case when there are two links which are in opposite directions. So, there are flow which are in opposite directions, and the travel time um, on one of these links is also getting affected by the flow on the other link. Okay. So, we wanted to argue that the optimization formulation for this equilibrium with link interactions has unique solution. Okay. So, in order to argue that we need to we can, if we are able to show that the objective function is strictly convex, then we will be able to argue that the solution will be having a unique minimum. The reason being that we already know that the constraints of the proposed optimization formulation are linear, so they are convex. And if the objective function is strictly convex everywhere, then it also implies that it is convex everywhere and it is also strictly convex at any stationary point, and therefore the solution of the first order equations is having a unique minimum. Okay. So, let us start to prove that this objective function uh, is strictly convex everywhere. So, for that we need to show that the Hessian matrix of this objective function is positive definite everywhere. Okay. Now, recall that the first derivative of this objective function zx with respect to the flow on link A is given by the travel time on this link. Okay. So, this we had seen in the last lecture. So, now in order to obtain the second derivative, so first we will be taking the derivative of the objective function with respect to the flow on link A and then with respect to the flow on link B. So, this is what we actually get when we do that. So, since we already know that the derivative of the objective function with respect to the flow on link A is the travel time of that link A. So, from this we get to this point here. So, now we need to take the partial derivative of the travel time on link A with respect to the flow on link B. Okay. Now, note that the travel time of link A is a function of two things. First, it is the function of the flow on link A here, and it is the function of the flow on link A dash, which is the opposite to this link A. Okay. So, therefore, this quantity will be non-zero only when if the link B is the same as link A, because in that case, since the travel time of link A is the function of the flow through link A as well as the flow through the link on opposite direction A dash. So, since this travel time on link A is dependent upon this x A, so therefore, this will not be 0 here, and similarly when this link B is suppose link A dash, which is the one which is opposite to link A. So, since T A is also a function of x A dash, so therefore, we cannot ignore this quantity. However, if link B is any other link apart from A or A dash, then this quantity will be 0. That is, the second derivative with respect to the flow on links A and B will be 0 if B is neither link A nor link A dash. Okay. So, we have obtained the second derivatives expression here. So, now we are ready to put together the Hessian matrix of this objective function. So, what we will do here is that we will order the links that are there in this network in such a way that each link is adjacent to the link that is representing the opposite traffic movement. Okay, that is, for example, if there are suppose 4 links here with us 1, 2, 3 and 4, okay. And suppose 1 and 2 are opposite to each other, and links 3 and 4 are opposite to each other. So, we will be putting these links 1 and 2 together, and then we will be putting links 3 and 4 together. I mean, the ordering will be in such that first link will be this, then this, then this, then this, okay. Suppose in another example, if it was the case that suppose link 1 and link 4 were the links which were in opposite direction to each other, and then links 2 and 3 were the ones which were in opposite direction to each other. So, the ordering in which we will be writing down the rows and columns of this Hessian matrix that we will show will be in this order, that the first row and first column is corresponding to this link here, then the second row and the second column are corresponding to this link, and then the third row and third column are corresponding to this link, and the fourth row and fourth column are corresponding to this link, okay. So, given this order, that is the links which are in opposite direction are put side by side, the Hessian matrix of this objective function, that is this here, can be expressed as follows. So, now you can see here that this Hessian matrix has these small matrices also. So, these are block matrices here. So, the gradient square here for this pair A comma A dash. So, this is given by this 2 cross 2 matrix here. So, for example, this grad square 1 comma 1 dash, okay. So, it is actually consisting of the elements corresponding to the links 1 and 1 dash, given that 1 and 1 dash are opposite to each other, okay. So, then here we first take the partial derivative of the travel time on the first link with respect to the flow on this first link, then we take the partial derivative of the travel time on this 1 dash link with respect to the flow on link 1, and then we take the partial derivative of the travel time on link 1 with respect to the flow on link 1 dash, and then we take the partial derivative of travel time on link 1 dash with respect to the flow on link 1 dash, okay. So, this is what we have here. So, another thing to note is that this is not a scalar 0 here. So, you can see that this 0 has been made bold. So, this 0 represents a 2 cross 2 matrix of zeros, okay. So, this 0 is this matrix here, okay. And you can guess that why we are getting these kind of matrices, because see the travel time on the first link will only be a function of the flow through that link and the flow through the opposite direction link, which is 1 dash, okay. So, for that link, only the partial derivatives with respect to x1 and x1 dash, which are shown in the first 2 rows here, they will be non-zero, okay. All the other things will be 0 here. So, that is why this is 0 here, and all the other entries below are 0 here, okay. Similarly, the travel time on this link 1 dash will only be non-zero with respect to the flow on link 1, which is opposite to link 1 dash, and with respect to the flow on link 1 dash, okay. So, therefore, all the other entries below this will be 0, okay. So, that is why we have the 0 matrices which are corresponding to two cross 2 matrices of 0 being shown here. Okay. Similarly, the flow through link 2 here, which is represented by, which will be part of this small matrix here. So, here the travel time on link 2 will only be dependent upon the flow through link 2 and the flow through link 2 dash, which is opposite to 2. Okay. So, only those entries will be non-zero, and since it is the travel time on link 2 is not a function of the flow through link 1 and link 1 dash and link 3 dash. So, this is 0, and similarly the entries below this are also 0. Okay. So, this is how we get this Hessian matrix corresponding to this objective function here. So, I have just written this again because we are still discussing this here. So, this structure of this Hessian matrix is a block diagonal matrix with each block given by the 2 cross 2 matrix, which is this one here. Okay. So, you can see that there are these different blocks here, which are themselves 2 cross 2 matrices in this large Hessian matrix. Okay. So, that is why it is called a block diagonal matrix, and only along the diagonals these blocks are non-zero. Okay. Everywhere else you will be having these 0 matrices which are of 2 cross 2. Okay. So, here it will be 0 0 0. So, the dimension is 2 cross 2 here. So, everywhere except the diagonal you will be having the 0 matrices. Now, note that each of these 2 cross 2 matrices is positive definite if its diagonal entries and its determinant are positive. Okay. So, we are right now talking about these 2 cross 2 matrices here. So, we can first see that these 2 cross 2 matrices are positive definite, and actually that also implies the positive definiteness of the large Hessian matrix. So, to see that this block matrix here, which is of 2 cross 2 is Hessian, is positive definite. So, we can see here that the diagonal entries here, they are positive, because this is the assumption that we had made, that the rate of change of travel time with respect to the flow on that link is positive. Okay. So, this is one of the assumptions that we had made in order to argue that this objective function is strictly convex everywhere. Now, what remains to be argued in order to show that this block matrix is positive definite is that the determinant of this matrix is positive. Now, see, the determinant of this matrix is this here. So, we multiply this with this minus this with this. Okay. So, this is what we get here. Now, this is positive. Why? Because previously we had made this assumption that this is greater than okay. So, we had made this assumption here. Okay. So, this is one thing that we know, and same is also applicable for the link A dash also. So, we can also say that dT A dash with respect to the flow on link A dash is greater than dTA with respect to the flow on link A dash. Okay. So, we are saying that this first quantity is greater than this quantity, and we are also saying that this quantity is greater than this quantity. Okay. So, therefore, together the product of these two terms will be greater than the product of these two terms. Okay. So, this is what it has been said here. Okay. So, this is the same thing that I had said. So, since this is applicable for all links A, so here it also includes the A dash. Okay. So, given that these 2 cross 2 block matrices are positive definite, the Hessian matrix, which is a block diagonal matrix where each block is positive definite that we have argued, will also be positive definite. Okay. So, this we are not proving it here, but this has been left as an exercise here. So, what we have showed is that these 2 cross 2 block matrices are positive definite, and that will imply that this Hessian matrix, which is a block diagonal matrix where it only has these non-zero entries along the diagonal, and all of these entries are block matrices, and everywhere else we have 0 matrices. So, this will also be positive definite. Okay. So, given that this Hessian matrix is positive definite, the objective function is strictly convex with respect to the link flows. Okay. And therefore, it can be concluded that the optimization formulation has a unique minimum. Why is that? Because the constraint set of the optimization formulation is convex, and since the objective function is strictly convex everywhere, so it is also strictly convex at the stationary solution, and it is convex everywhere. Okay. So, therefore, we have a unique minimum for this optimization formulation. Now, again to remember is that the solution of the first order conditions is unique with respect to the link flows and not the path flows here. Okay. So, this uniqueness that we are arguing for this problem is with respect to the link flows and not with respect to the path flows. So, this we had also said when we were discussing the deterministic user equivalent case when there were no link interactions. So, since this is an extension of that version of user equilibrium when there are no interactions. So, it has to be the case that again the uniqueness is with respect to the link flows and not the path flows. So, all of this discussion that we are doing related to the equilibrium with link interactions. So, again this is another good reference for this is Sheffy's book on urban transportation networks. So, one can always refer to that as well. So, how to now solve this optimization formulation that we have seen? So, convex combination algorithm that we had introduced to solve the deterministic user equivalent problem when there are no link interactions can be easily be extended to solve this case also. So, in the convex combination algorithm there are various steps. For example, one of the steps is to find the direction. So, in that one we usually solve a linear program there. Okay. And in this case the linear program will stay the same, just with the change here that now given that the travel time on link A is not just the function of the flow through that link, but it is also function of the flow through the opposite direction link. So, TAN will be actually TA and it will be function of XAN and XA A dash n. Okay. So, that is the only change, everything else stays the same. I mean the constraints that are there in that linear program, although that are not shown here, but those are the same. Okay. So, this above function is minimized subject to the flow conservation constraints in Y. Okay. So, the constraints are the same as before, the objective function is also the same as before, just the only difference is that this travel time here for link A at the nth iteration, which is this here. So, this is obtained when you plug the flow values of link A as well as of link A dash, which is opposite to link A for that nth iteration in the expression for the travel time of link A. Okay. So, the solution of this aforementioned program, that is this linear program, can be found by simple all or nothing assignment. Okay. So, this also we have seen before. So, since the travel times are constant in this direction finding step, so we do not even need to solve this linear program. The solution can be easily found out by assigning all the flow for every given OD pair to the path which has the shortest length. Okay. And once we do this for every OD pair, then we can calculate what are the flows for different links. Okay. And that is the solution of this direction finding step. So, the next step that comes in the convex combination algorithm is the optimal move size step. So, there once we obtain the solution from the previous step of direction finding, so then the target is that how much should we move from the current solution xn towards that solution yn which we obtained from the direction finding step. So, for that we have this scalar alpha n. So, that has a value from 0 to 1. So, 0 corresponds to the solution xn that we originally have at the nth iteration, and yn is the solution that we obtained from the direction finding step. So, if alpha is equal to 0, so it is corresponding to xn. If alpha is equal to 1, then it is corresponding to yn. So, we want to see that what is that point in this line segment joining xn and yn where the objective function value takes the least value. Okay. So, that is also an optimization problem. So, that optimization problem becomes the following when we have these link interactions. So, what we have done here is that in the objective function that we saw for this optimization problem in the last class. So, there we have replaced wherever xa was there with respect to xa n plus alpha times y n minus xa n, and wherever xa dash was there, we have replaced it with x a dash n plus alpha times y a dash n minus x a dash n. Okay. And now we need to minimize this objective function with respect to the constraint that alpha lies between 0 and 1. So, all the other steps of convex combination algorithm are the same as that mentioned for the basic user equilibrium. So, let us now consider this simple 3-link network here. So, here there are 3 nodes and then there are 3 links here. So, the delays to traffic on link 2 would be influenced by the flow on link 1 and vice versa. Okay. So, what we are assuming here is that if the flow on this link, that is link 2, increases, then it will also have effect on the travel time on this link because of this common intersection that is there. Okay. Because not all the flow on link 1 will be able to easily go to link 3 if there is a lot of flow that is coming from link 2 towards the intersection. Okay. And same holds for the link 1's flows effect on the travel time of link 2. Okay. So, due to the geometry of this intersection can be expected to be symmetric. That is, whatever change the travel time happens on the link 1 with respect to the change in the flow on link 2 will be the same as whatever the flow on link 1 introduces the change in the travel time on link 2. Okay. So, suppose that we have the expressions of the travel time for these 3 links given to us here. Okay. So, you can see that the travel time of links 1 and 2 are function of not just x1 and x2 respectively, but they are also a function of the opposite direction, the other pair of links, that is x2 and x1. Okay. So, although these two links 1 and 2 are not opposite direction, but whatever theory we have developed here for the links which are having pairwise interactions, that holds here. Okay. So, you can see that the travel time on link 1 is a function of both the link 1 and 2 flow, and the travel time on link 2 is function of the flow on link 2 and 1. Okay. So, that is also you can see here. And suppose it is given to us that 5 units of flow is going from origin to destination. Okay. So, now we know that whatever flow wants to go from O to D here, so all of that will have to pass through link 3. Okay. So, the flow through link 3, that is x3, will be equal to 5. Okay. And if x3 is equal to 5, so since T3 is equal to 3 plus x3, so it is equal to 8. Okay. So, we know what will be the flow through link 3 in the equilibrium, and therefore, we also can calculate the travel time through link 3. So, let us now focus on links 1 and 2 here. Now, let us assume that both the links are used at the equilibrium, that is the travel time on link 1 is equal to the travel time on link 2. Okay. So, if we use that equation and we also use the fact that x2 is equal to 5 minus x1, this is the solution we get. So, we can let us quickly see how we get this. So, T1 is equal to 2 plus 3x1 plus 2x2. Okay. And we are equating it to the expression for travel time of link 2, which is 4 plus 2x2 plus 2x1. Okay. So, this is one equation, and the other equation that we have is that x2 is equal to 5 minus x1. Okay. So, now here actually this one is very easy. So, these two terms get cancelled here. So, we get that x1 is equal to 4 minus 2 equal to 2. Okay. And since x1 is equal to 2, x2 is equal to 5 minus 2 equal to 3. Okay. So, that is how we get x1 star is equal to 2 and x2 star is equal to 3. Now, if that is the case, then the travel times at the equilibrium are equal to 14 for both the links, because let us substitute the values here. So, the travel time on link 1 will be equal to 2 plus 3x1 plus 2x2. Now, x1 is equal to 2 and x2 is equal to 3. So, this is equal to 2 plus 6 is equal to 14. Okay. And similarly, for the travel time on link 2, we can write down the expression 4 plus 2x2 plus 2x1 here, which is equal to 4 plus 2 times of 3 plus 2 times of 2 here. Okay. So, 4 plus 6 plus 4 here. So, again this is coming out to be 14. Okay. So, the travel times on both the links are coming out to be the same and equal to 14. So, this is the solution that we obtained by considering these cases manually. Okay. But when this network is complex, then using this approach may not be trivial, because there might be many OD pairs. First of all, in this example there was single OD pair, and there might be many paths connecting every OD pair, and these paths might be very overlapping. Okay. So, considering these cases, that let us first assume that for this OD pair, suppose these set of paths are having flow, that is they are getting used, but these set of paths are not getting used, and let us make a similar assumption for another set of paths for another OD pair and so on. So, there will be a lot of cases that you will have to consider. Okay. So, using this approach to solve the equilibrium solution is not an practical way when we have a very complex network. Okay. So, that is why we have developed the optimization formulation to obtain the solutions for those complex cases. So, we will be seeing how we can check the solution for this problem using the equivalent optimization formulation. So, that we will be continuing in the next lecture here. Thank you.